Hey everyone. So the task is for the robot to autonomously knock down all the plastic bottles while ignoring the other objects. Now I've implemented this with YOLO V8 and mask-rcnn. So YOLO is much faster, but it's a bit less reliable. So mask-rcnn was able to identify the bottles in 100% of the trials, while YOLO kept missing that blue and pink bottle at the top of the screen, the one that's just been knocked over. So in the rest of the video, I will show you how I made the robot car for autonomous task completion. Hey everyone, so today I'm going to make a robot buggy for autonomous task completion. And the first thing I'm going to need is this robot chassis that I got off AliExpress, and this one's just one I've ripped off an old project. And these things, they come with these little things that connect to the motor, these little round things that look like that, and you can use these to attach a rotary encoder. So this is the rotary encoder that I'm going to use, and this is going to be used to measure how far the robot's traveled, how far the buggy's traveled, and also the angle that I want to turn it. So I can tell it how far to go and what angle to turn at using one of these. And then the other thing I'm going to need for this project is, of course, a MOSFET H-bridge dual motor controller, and I've used these in a few projects. And then of course I'm going to need an ESP32, which I'm going to use to connect to the rotary encoder and the dual MOSFET motor controller. And then the last thing I'm going to connect is this stereo camera that I made in the previous project. So this is going to be doing a lot of the inference. So I'll connect all that up and we'll see how that goes. Hey everyone. So I've put the car together now, and I've got the two motor controllers here, one for the front and one for the back, and I've got the ESP32, and as well I've got the rotary encoder. So I'll just get a bit more of a close-up on that, and you can see that's the rotary encoder there. And what that does is that counts the wheel revolution. So it does 20 interrupts per wheel revolution. So before I continue, I'm going to give a brief explanation of how I've got the motor controllers connected and how I'm powering it. So I'm using two motor controllers, and if we zoom in a bit, we can see them a bit better. So the left side of the motor controllers are the inputs, and the right side are the outputs to the motors. So for the inputs, I've got them all connected together for corresponding inputs. So I've got input 1 of motor controller 1 connected to input 1 of motor controller 2, and PWM of motor controller 1 connected to PWM of motor controller 2, and so forth. And the reason I've got them connected together is, one, I just need one pin from the ESP32 for those two inputs, and the most important reason is because I want to turn the two left wheels always in the same direction and the two right wheels always in the same direction. And then for the outputs, I've got the outputs of this one connected to the front motors and the outputs of this one connected to the back motors. And so output A are connected to the left motors, and output B are connected to the right motors. And I'll put all the pin connections as a comment in my code. And the reason why I'm using two motor controllers instead of one, I could have one motor controller just driving two motors, each output connected to two motors, but I'm just worried I won't be able to draw enough current from one motor controller to power the car. All right. And speaking of power, I'm using, for the motors, I'm using this dual cell LiPo, which puts out about 8 volts fully charged. It says 7.4 volts there, but that's normal charge. And then to regulate the voltage, I'm using this buck converter. It's an LM2596, so I've got the voltage set at about 6.5 volts. and by the time it goes through these motor controllers, it's around about 6 volts into the motor. And then to power the electronics, I'm using this 18650 battery shield, which has a built-in converter and puts out a 5 volt signal. And then I've got the 5 volts running it along this rail and this rail here, and then I can just connect everything up like that. So we'll power that up and we'll see how it runs in the next scene. So I've loaded a sketch onto the ESP32, which includes an HTML file which allows me to specify how far I want the car to move and the angle I want it to turn. So I'm going to trail that out now, and hopefully that'll work. I'll show you the sketch and I'll show you how it works in the web browser as well. And then once I've done that, I'm going to attach my stereo camera to the car, and we'll have a look at it, how it works with the stereo camera, just for visualization. And then once all that's working, we'll connect the output, we'll stream the stereo camera into Python and get the robot to perform some autonomous tasks. So I've got the car powered up now, and I've just got it suspended so its wheels are just off the ground, and I'm going to drive it forward and backward. And the reason I'm going to do that is just to check that I've got the polarities of the motor connected correctly to the motor driver. And so with these motors, you know, is it this way, is it this way, is it this way, is it that way? You know, so it's often difficult to get the polarities right the first time. So I'm just going to make sure the motors are going in the right direction when I press forward and backward. All right, so I'm just going to press forward. Okay, so we see these two are spinning in opposite directions. So I'm going to have to reverse the polarity on one of those. But these two are spinning. Well, this one's spinning in the right direction and this one's not spinning at all. So there must be a wire loose somewhere. So I'll fix that all up and then we'll get the car moving. So I've wired everything up and I've got it all powered up now. And this is the interface for the car here. And these are the forward, left, stop, right, backward, and speed controls that I got off Random Nerd Tutorials. And here is the distance, that's how far in centimeters I want it to go, and the angle, how far I want it to turn. And these ones use the rotary encoder. These are the placeholders for the cameras, which I haven't put on yet for the stereo camera. But this is a fun little sketch even without the stereo camera, because you can actually tell the car how far you want it to move in centimeters and how many degrees you want it to turn left or right. So like I said, it's a fun little sketch, and we'll test it out now. So the tape measure that's next to the car is set at 1 meter. So I'm going to tell it to travel 100 centimeters and we'll see how far it goes. So that's embarrassing. First thing I need to do is turn the speed up, because I've got the speed set at 0. Okay. Alright, so I'll enter 100 centimeters and we'll see how far it goes. Now I'm going to turn it 90 degrees, left turn 90 degrees, and turn it again. So it should be turned now the other way, and now I'm going to bring it back 100 centimeters, so it should end up almost where it started at. And that's working really well. And then the other thing I wanted to say is that you have to have a capacitor across the positive and negative inputs to the rotary encoder. So this is the rotary encoder here, and this is the positive input for the rotary encoder, and this is the negative, and this is a 230 microfarad capacitor. Any value around about 100 microfarads should do. And the reason you need a capacitor is to filter out any noise on the encoder, because the encoder sends 20 pulses per second to the ESP32, and these pulses come in as interrupts. So on a rising signal, it triggers an interrupt, and if there's noise, it's going to think that it's an interrupt. So if there's noise on the signal, it's going to think that the input is rising, and this is an interrupt. So what will happen is you'll enter like 100 centimeters, and it'll only move 30 centimeters. So that was happening to me, and then when I put this capacitor in here, that solved the problem. So that's really important. So the next thing I'm going to do is I'm going to connect the cameras. The left camera will show up here, and the right camera will show up here. And then after I've connected the cameras, I'm going to see if I can do some inference to get it to move and turn on its own based on the camera input. This is the stereo camera here, and I went over how I made this in the previous video, which I've linked in the description. So very briefly, all I've done is I've just soldered on these female header pins onto a piece of perf board, which I'm using to hold the cameras securely in place and keep them horizontally aligned. And at the back of the perf board, I've just soldered on a 5-volt and an earth wire. So when I plug these into the perf board, it's only the power pins that are connected. So if I want to flash it or anything, I can just take it out and flash it and then put it back, and it works really well. So that's the stereo camera. So I've mounted the cameras just on the front of the car like that, and I'm going to test this out now. Hey everyone, so I've got the camera set up, and you can see the left camera here and the right camera here, and that bottle is about 1 meter away from the vehicle, and I'm going to try and knock it over. So first thing I'm going to do is increase the speed, and then I'm going to enter, let's say, 105 centimeters and see if we can knock that over. Let's just try 100. Alright, that was almost perfect. Hey everyone, so I've got the car positioned on my desk now, facing this bottle, which is a bit to the left. So I'm going to see if I can get it to turn automatically towards the bottle and drive to the bottle. So I'll show you that on the computer screen. Alright, so I've got the car set up with the bottle a little bit to the left. So the idea is for the car to turn a bit left and move to the bottle autonomously when I run this Python script. So let's run it and we'll see what happens. Okay, this is the left image and this is the right image. And now we'll do the inference. And that was perfect. So the object is to knock over the 3 bottles, ignore the mug and the toy car, and then return back to the middle spot. So in this scene, I show the task completion with the mask-rcnn model. And the mask-rcnn model is quite slow, so I've had to speed up the video in parts. And I've indicated where I've speeded it up. In the next scene, I show the task completion with the YOLO V8 model, and I didn't have to speed up the video at all for that. So I'm showing that in real time. Now you're probably wondering why I went with such a task as knocking over plastic bottles. And the reason is because I wanted to make a robot that could pick up recycling bottles, but I didn't have the resources for a gripper or a robot that could carry it. So knocking over plastic bottles was just like a substitute for now, just to test the concept until I get the resources. This scene shows the object segmentation and distance estimation from both the left and right cameras. And when the car sees a bottle, it tries to knock the bottle down by moving the estimated distance plus an extra 3 centimeters, and then it returns back to its original position, hopefully. And if it sees either the cup or the toy car, then, or another object in the background, then it doesn't do anything, it just turns 5 degrees. So it keeps doing that until it's knocked over all the bottles. And I'll discuss some of these images in more detail in the next scene. Hey everyone, so I'm just going to go over some of the images from the camera, and some of these we saw in the last scene. And on the left here we've got the left camera, which I call left eye, and on the right here we've got the right camera, which I call right eye. So the bottle is fairly well segmented, and the distance estimate is 35.4 centimeters, and that's fairly accurate. So next, the car turns about 5 degrees, and it detects a cup. And it estimates the cup is 55.9 centimeters, and then it turns another 5 degrees and it detects the cup again and a toy car, and the cup it estimates is 54.3 centimeters, which is fairly accurate, and the car it estimates at 50.8 centimeters, which is also fairly accurate. So I'm going to show you an example now of where the distance estimation didn't work very well. So here it's identified a refrigerator, which is actually an electric water gun on top of a water bottle, and it's identified this as a refrigerator, but that's not the issue. It's estimated that it's 210 centimeters away, and this is about 1 meter away from the camera, so about 100 centimeters. Now the reason why the error is so large and tends to increase for objects that are further away is because the distance from the camera is inversely proportional to the pixel difference between the left and the right images. So when the objects are closer, the pixel difference is large. So say we've got a constant error of 2 pixels, and when the objects are closer, they're 100 pixels apart, then the 2 pixels error is only going to give us a 2% error in our distance. But when they're further away, they're 2 pixels apart between the left and right image, then our 2 pixel error is going to give us 100% error in our distance measurement. And the other thing is, probably just as importantly, is I've only used the bounding boxes. I haven't used any of the segmentation mask or any color features. So I could tweak it a little bit by shifting the bounding boxes to try to see where the best match is between the two objects. And the reason why my motivation for using object segmentation rather than just taking patches in the image, which is how it's usually done, was because taking patches in the image and then shifting them across basically so you can see where the best match is doesn't work in cases where you've either got a monochromatic surface where the surface is like just a single color, or you've got a highly textured surface. So I thought this would work out a little bit better. Hey everyone, so I'm going to go through some of the code with you now, and I'm going to start with the Python notebooks, and then I'm going to describe the ESP32 sketches. So there's 2 Python notebooks. There's one for the mask-rcnn model and one for the YOLO V8 model. And I'm just going to talk about the YOLO one now. I'm going to put them both up on the GitHub repository, but I'm only going to talk about one of them now. So the first thing we do is we do our import our packages, and the Ultra Analytics package is the one that contains the YOLO model. And then these are all just standard packages. The stereo image utils file I'll put up on the GitHub, and that just contains a lot of the code, a lot of the auxiliary functions for this notebook, which I didn't want to actually put in the notebook just because they'd clutter it up a bit. Now these set functions, they're the ones that send the HTTP request back to the ESP32, and I got these functions from the Hackster.io project that I'll link in the description. So they're all self-explanatory. This set angle 1 sets the angle of the car, and I've put the equivalent JavaScript function here as a comment, just so you can see more clearly what it does. And then we initiate our YOLO model, and there's 5 different models, all of different sizes, and I'm using the M model, which is medium. So there's small, medium, large, extra large, and N, which is like very small. So they're all listed here in a table, and it tells you the number of parameters and the mean average precision. And for the M model, the mean average precision is 50.2. And when I used it, I found that the L and the X model didn't actually give any improvement for what I wanted to do, but the M model was a great improvement over the S and the N models. And then I guess with the mask-rcnn model, for the box, for the bounding boxes, the mean average precision is 47.4. So URL left is the URL of the left camera, URL right is the URL of the right camera, and URL car is the URL of the car, and FL and tan theta are calibration parameters of the camera that I calibrated in the last video. And then this is our main loop, and this does basically the inference. So cap left is the left camera, cap right is the right camera, and then I capture the frames, and then I release the camera, and then I have to start the video capture up again. And the reason why I don't just keep the video capture open and keep capturing the frames is it was doing something weird where it was putting all the frames in a queue, and because it was taking time to do the inference, it wouldn't get the most recent frame, it would get the next one from the queue. And I'm sure there's more efficient ways to get the most recent frame, but this way seemed to work. So I show the left, what I call the left eye, which is the left camera, and I show the right eye, which is the right camera. And then out L is the output of the left camera from the model, from the YOLO V8 model, and out R is the output of the right camera, the right frame from the YOLO V8 model. So I check that there is something detected. If the boxes are empty, are just empty lists, then nothing has been detected. So if nothing's been detected, then I move the car over 10 degrees and then I scan again. And then CNT is just a control for debugging. So if I want to debug this, then I can just set this to 1 if I don't want to run this part of the loop. So once I've done my object inference, I get the detection boxes. So det0 are the detection boxes from the left image, and det1 are the detection boxes from the right image. And then I get a cost. So a cost is like a probability of assigning every object in the left image to every object in the right image. So for each object in the left image, I calculate how likely it is that each object in the right image is the corresponding object. And the way I do that is I look at the horizontal shift. Like if it's vertical, then that's probably not likely to be the same object, and the size, and of course the class label. And I've described all that in the previous video. And then the tracks, these optimize from the cost. So these choose which ones go with which ones based on the cost matrix. And then I take the distance of the top left corner of the bounding box and the bottom right corner to the center. So the horizontal distance, and I use the corner that's closest to the center as like the anchor. So I use that as the point of measurement between the corresponding bounding boxes between the left and the right. And the reason I use the one that's closest to the center is because if it's like if one's slightly occluded, like off the screen, then it won't be very accurate to use another measure. So NM0 are the labels for the left box and NM1 are the labels for the right box. And then here I check if there's a bottle detected, and I check if the bottle is upright. So basically all the bottle upright does is checks that it's taller than it is wider. And then I move it an angle. So so I just, if it's to the left, then I move the car to the left, and if it's to the right, then I move the car to the right. And then I calculate how far away each object is. This is the formula here, which is just the standard stereo imaging formula for calculating the distance between, calculating how far an object is based on the pixel distance between the left and right images. And then I just do my visualization, and I move the car. So I move it +3. So I add 3 centimeters to the detected distance to make sure it knocks over the bottle. And then these are the key presses. So if an escape key is pressed, then I brake. So so that's it. And if you've got any questions, just leave them in the comments. And next I'll describe the sketches that go on the ESP32. This is the sketch that I've uploaded to the ESP32 that's controlling the car, and I'm just going to go over a few things very briefly with you. The sketch should be on GitHub, and you can read it. If you've got any questions, just leave them in the comments. So I guess first thing is that this comment here just shows you what pins I've used. These are the ESP32 pins. These are the motor driver pins, and then the rotary encoder interrupt pin I've got connected to ESP32 pin 23. And then these are like the real world parameters. So the number of holes, which is just corresponds to the number of interrupts per revolution. So 40 interrupts means that the wheel spins 1 revolution, which is 21.05 centimeters. And then the holes are here, and there's 20 holes, and the reason I'm using 40 is because there's basically 2 interrupts per hole. So what I did with the rotary encoder is I triggered the interrupt on a change. So before I had it triggering on a rising, and then I was getting 20 interrupts per revolution, but when I did it on a change and getting 40 interrupts per revolution, it seemed a little bit more precise. And it didn't make too much difference for moving forward or backwards, but for turning, it did make a little bit of difference. It tended to slightly overshoot a little bit if the number of interrupts per revolution was a bit low. I mean, maybe that was just my motors, the quality of my motors, but it did improve a little bit by doing this. So now this is the turn robot function, which basically takes in feet, which is a number of degrees, to turn in radians, and turns at that amount. It sets counter 2 to 0, which is the counter that gets incremented every time there's an interrupt. So we can tell how far it's moved by multiplying counter 2 divided by the number of interrupts per revolution times by the total distance of the revolution. And then once we exit this while loop, we just tell the robot to stop here. And the same with the distance. We have D2, which is basically our absolute distance to move. So if distance to move is less than 0, then we move backwards. If it's greater than 0, then we move forwards. And so while we haven't moved that distance, we just keep moving, and we're interrupting the counter. We're incrementing the counter in the interrupt. So as we move, the counter increases, and then once D2, which is an increasing function, the counter reaches how far we want to move, we stop the robot and reset the counters. And then the other thing I wanted to show you is here, I've used a static IP, which I've configured the parameters here. And the reason I'm using a static IP is because I don't want to have to check my IP every time I turn the car on, because I've got I've got commands running from Python to the car, or if I'm using the web interface to drive the car, then I'm going to have to check what IP has been allocated. So I'm just going to stop with the explanation there because there is a lot of other code to get through. Like for example, the ESP32 cam sketch, which I'm going to go through next. Hey everyone, so I'm just going to go over the sketch that I've uploaded onto the ESP32 cam, and I got the sketch from Random Nerd Tutorials, but I did make a couple of changes. So the first change I had made was a static IP, and you need a different static IP for each camera, so a different static IP for the left camera and a different static IP for the right camera. So all I need to change is this number here. And then the other change I've made is to the stream handler. So I had to swap a couple of lines around to get the stream handler to work with Python. So in the original sketch, this line here was actually down here. But then I had to put it up there because the Python code seems to expect the stream boundary first, and then it worked with Python. And then the other change I've made is I've added a command handler here to handle the HTTP requests from the Python code. So requests to set the resolution, which is really the only one that I'm using. And the other request is to set the quality, but I haven't used that. So then you have to register the command handler in here somewhere. Up here. So yeah, so that's it basically, and I'll put this up on GitHub. Alright, so thank you for watching, and hopefully I'll see you in the next video.